Hello everyone. Today we have Sankha Subhra Chakraborty from Math second year. He is interested in algebra geometry and today he will be talking about exact sequence and Lazard theorem. Over to you.
Thank you. Before I start discussing the actual content of my talk, I'll make a small comment on how I want all of you to think about universal properties. Every time I say universal property in this talk. So what is a universal property is essentially you start with some diagram and then you look at the collection of all objects which make that particular diagram commute. And then among this collection, we will assign some of them to be special in some sense. I will illustrate this via the first universal property that we have all learned back in school, in fact. GCD. So let's just work with integers, no need for needless abstraction. So if you take two integers a, b, then the diagram I claim at this moment are just these two integers. There's nothing else going on at the moment. And now the collection of objects that makes this diagram commute, whatever that means, are the collection of common divisors. And then the GCD is a common divisor D such that for any other common divisor C, C is going to divide D as well. So in the notation for product, it would look something like this. If I represent divisibility using an arrow, that C divides A, if I just denote it by this arrow, then I can write this. A, B. So essentially the point is, two things are going on. D itself makes this diagram commute, and for any other C which makes this diagram commute, there is going to be an arrow from D to C. And this notion can be formalized using the notion of limits and co-limits, but that is abstraction that we do not need for this talk. Okay, now I'll actually start. So I will assume everyone in the audience is familiar with what are vector spaces, abelian group with the left action of a field, scalar multiplication which satisfies distributivity, associativity, and identity element, fixing all elements. So I'll fix, instead of a field, a module is simply the same definition as you have for a vector space, but replace your field K by a ring. That's all. And for the sake of this talk, I will work with a fixed commutative ring with unity. So the axiom that we have for vector spaces, that 1 dot v is equal to v for all v in v, the same thing will be here. And all modules in this talk will be left arm modules, so I will not specify left arm modules separately. Even arm modules I may not specify sometimes because once again all modules will be considered over this ring R. Next, module homomorphisms. Again, once again, I will assume everyone knows what vector space homomorphisms are, which are precisely the k-linear maps. So f of a plus b is f of a plus f of b for all a, b in b, and f of alpha x is alpha f of x for all alpha in your field and x in your vector space. So just replace k by r and you get the definition of a module homomorphism. I will use these terms interchangeably: module homomorphism, module morphism, module map. Unless stated otherwise, a map between modules is going to be a module morphism. If it is something else like a bilinear map or a set function, I will make sure to specify that separately. Exact sequences. So suppose F, G, H are modules, and suppose we have module homomorphisms alpha and beta as such. Then we say that this sequence is exact at G if the following holds. That's the definition. Now sometimes we will have longer chains of modules, longer chains of morphisms. In that case, I will say that the entire sequence is exact if it is exact at each of the intermediate steps. So an easy result that you can all try to prove if you want is is just a trivial application of your first isomorphism theorem. But the point of writing this down is that exact sequences of this form 0, f, g, h, 0, these are called short exact sequences, which I will abbreviate as SES. And this is what I meant. This sequence being exact means it is exact at f, exact at g, and exact at h. Next I will talk about something that I will use quite a bit, direct sum. So suppose we have an indexed collection of modules indexed by some indexing set. Then the Cartesian product of M alphas is the standard Cartesian product that we know of, which is the collection of functions from the indexing set to the union of these M alphas, such that the when you evaluate the function at alpha, you get something in M alpha. So essentially, you can think of them as sequences indexed by the indexing set alpha. The distinction that we will make for direct sum is that we will necessitate that that only the functions with finite support are allowed. So we will not have unrestricted sequences. We will only have sequences for which all but finitely many of the terms are 0. And the notation for direct sum is going to be this. Sometimes I may not write alpha, sometimes I may just write the indexing set. And the module structure here is quite clear. You do addition and scalar multiplication pairwise. As in the elements of your Cartesian product are functions. So f plus g, you define it as f of x plus g of x at every point, and similarly for scalar multiplication, because M alphas are modules. So each fx is going to be some module element. Next, we have the given a direct sum modules. We have inclusion maps. And it is just going to send M to E sub M. And E sub M is a function. We will take the value M if x is equal to beta and 0 everywhere else. So essentially, you take a module element in one of these modules. The most natural way to represent it in the direct sum is the element which is M at the beta coordinate and 0 everywhere else, which is just what this definition says. And the point of these canonical inclusion maps is the following. So it turns out that the direct sum is in fact a coproduct in the category of R modules. What the coproduct is in general is whatever I'm going to define right now. So the direct sum, as we have defined it along with the inclusion maps, satisfies the following universal property. Given an R module Z and a collection of maps G beta from each n beta to Z, there exists a unique G from the direct sum to Z such that the following diagram commutes. This diagram commutes for all beta in your indexing set. Drawing this arrow just means injective morphism, nothing more. The point of making this arrow dotted is that this, I want to emphasize that this arrow is induced by each of these arrows. And again, that's another thing I want you to keep in mind about universal properties, is that they allow us to start with some collection of maps and then in some natural sense build a map, essentially coalesce the information of all of those maps into a single map into a single object, which is sort of what we do with, okay, maybe I should stop the GCD example, but even with GCD, but fine. Next I will talk about splitting of exact sequences. In particular, splitting of short exact sequences. So let us take a short exact sequence. Let me call these maps alpha and beta. We say that this sequence is split if any of the following conditions hold. There is this isomorphism S from C So recall what it means for the sequence to be exact. I think I still have it written down. Alpha is injective and beta is surjective. So beta is surjective, which means as a set map it has a right inverse. But the issue is that all right inverses may not be module morphisms. So that is precisely the requirement, that there exists a right inverse which is in fact a module morphism. Analogously, alpha is injective, so there will exist left inverses, but there may not be morphisms in general. So when there is such a morphism, a left inverse which is a morphism, that is another condition. And thirdly, the following diagram. Oh, and I guess I have not really mentioned what it means for this diagram to commute, but all that means is that G composed I beta is the same as G beta for all beta in the indexing set. And in general, that is what it will mean when I say that a particular diagram commutes. That you start somewhere, all the paths you can take to the end, they will be the same as set functions, compositions. Exact rows commutes. Don't have much space left here, so I'll draw the diagram here. This is notation for isomorphism. So essentially the third condition is that there exists an isomorphism from B to A direction C such that this diagram will come in. And this is exact by construction. These maps are the obvious maps. This is the obvious inclusion map. You send the element A to A comma 0, and here you send the element A comma C to C. And these maps, I guess I should have mentioned with at least once. Whenever we have a short exact sequences, we do not have to specify the maps at the beginning and the end ever, because like, okay, the generalization is that notion of an abelian category where the zero object is both terminal and initial. But essentially, if you have the zero module, there can exist only one module morphism from 0 to, a unique module morphism from 0 to any module, and similarly, there will exist a unique module morphism from any module to the zero module. So that is why those maps never have to be specified. There can be only one such. So this is exact sequences. Exercise. Show above the are equivalent. By that I mean these three conditions. And another remark I would like to make is that in tree, it is not enough to have any isomorphism from B to A direction C. The isomorphism should make these squares commute. That is important. Right. Next I will talk about tree modules. Right. We've seen in vector spaces, at least I'm assuming all of you have seen that every vector space has a basis. You can apply Zorn's lemma to show it is a consequence of Zorn's lemma. However, those of you who have taken module theory or are taking it right now have probably seen that not all modules have a basis. So that is what we want to resolve with three modules. We are going to define three modules as precisely those modules which have a basis. So we say that M is free if M is isomorphic to the direct sum of some number of copies of the base ring R. And R is of course a module over itself in the same way that a field is a vector space over itself in the trivial way. So the point is that over here on the right hand side we have basis elements EI, EIX, 1 x equal to I, 0 otherwise. So it is clear how these things form a basis. Like whatever element you want to represent, you scale these EIs and then add them together to get that element. And the point is that given this isomorphism, you can translate these basis elements into a basis for M, which will also be indexed by the indexing set capital M. And now we will do a quick result. And this is a result we've actually used a few times. Every exact sequence of this form is split. And this is not very hard. All of you can probably prove this if you try for some time. So this is surjective by exactness, but f has a basis. So we can simply pick, again this is also Zorn's lemma, we can simply pick inverse images of each of those basis elements in D. And now, I guess I should have talked about the universal property of free module before this, but there is no point. Okay, fine. The free module, you've probably seen this in free groups as well, or free ideal groups, whatever you've studied so far. That if you say, you've studied this in vector spaces probably, that for a linear map from a vector space to another, it is enough to specify where your basis elements go, and that specifies the map from the entire vector space to the module completely. And that is the property that we will keep abusing for free modules, because we have a basis. We will just specify where the basis elements go, and that is going to determine the module map completely. And that is essentially what we are using here. So each of the basis elements, we send them to some inverse image, and that extends uniquely to a right. Surjective is right inverse. Yes, right. So that is going to extend uniquely to a module morphism from F to B, which is in particular going to be that thing, this S, which shows that exact sequence splits. Okay, universal property of free module, no need to specify separately. Let's just do another simple Lazard. This is also another one that you will use eventually. Every module can be realized as the quotient for some free module. Okay, quotient is something I should have discussed, but I'm not sure if quotient vector space has been discussed. Because it was not formally discussed in our linear algebra course. I'll just talk about it once, but I won't go into too much detail because I don't really have time. I'll just take the universal property, I think, and be done with that. So given an R module M, let us look at the collection of maps from F to some other R module N, such that, and let us fix, okay, this not be N, fix N subset M submodule. Then the quotient M by N satisfies the following universal property, that given any module morphism from F to some other module K, such that the kernel of F contains N, there is going to exist a unique module morphism. This is just your quotient map, which sends every element to its equivalence class. There will exist a unique modular morphism from the quotient to K, which will make this diagram commute. I don't really have the time to talk about quotients in detail. But yes, every module can be realized as a quotient of some free module, and that is not hard. All we need for it to be a free module by the first isomorphism theorem. Okay, I guess first isomorphism theorem also may not have been discussed for the first years, but it's fine, I'll assume it. What was it about? Right. So it is enough, by the first isomorphism theorem, it is enough to specify a surjection from some free module to our arbitrary module M, and there is a very obvious choice. So I'll just prove it directly, no point wasting time stating this. So consider the free module whose basis elements are indexed. Okay, fix M, I guess that much I should get. So fix some R module M, and then let us consider the direction whose elements are indexed by the elements of M. There is a very easy surjection, and by the first isomorphism theorem, this shows that M is isomorphic to this direction quotiented by the kernel of this map. So equivalently, I can also state this result in this way. Okay, just erase the thing that would have been, which allows me to write down this equivalent formulation, but it is just one of the equivalent ways to define exactness for short exact sequences. So equivalently to this result, given R module M, there exists a short exact sequence it's the same exact statement. Here you take K to be the kernel take this map to be this surjection and take this map to be the natural inclusion of a kernel into this module. Okay, now we will talk about something new. So, fixed to our modules M and N, we will denote by form M comma N our linear maps from M to N. Simply this collection. However, of course, if it was just a set, there would not be much reason to care about it. We can put a module structure it in a very natural way, which is just pointwise, as you may have guessed. This is for all x in your module M and for all g in all N. Now I will discuss how we can make form behave like a functor. Now I do not have the time to specify what functors are, but for the moment just understand a functor as something that sends objects to objects. I'm keeping it somewhat vague intentionally, but and also sends maps to maps between the objects wherever you send them. Now in particular, this is what is known as a covariant functor because the direction of this arrow remains same, but there is no need for that specification here because both the functors we will be looking at today will be covariant, so this is what I will call a functor. And they satisfy two axioms, is that identity maps must go to identity maps and diagrams which commute initially must commute after applying the functor. So I'll just write down what I mean. So fix an R module M, then form M bar. What this does, it sends every R module A to the R module form MA, and it sends morphisms to a morphism from form MA to form MB. And this morphism, if this is called F, I'll denote this by F star, and F star is the most natural choice you could make. So we have, we have something in G. We want to map it something here. So what is G? G is something from M. I should not have written it here. It's fine. And then we have something here. So this is F. So the most natural choice for a module homomorphism from M to B is just the composition, which is precisely what this is going to be. So this is going to be F compose G. So F star is the map that sends G to F compose G. And then easy exercises are to verify the two following facts. For any A, identity on A is just the module homomorphism, the identity map as a module homomorphism on A. So, firstly, should I for all A, identity on A star is the same thing as the identity on form MA. And secondly, G composed F star is the same thing as G star composed F star. These are not concurrent by you. Next, exact functor. Again, no need to bother about what a functor is, just let us discuss it in the context of exact sequences. So definition, let F be a functor, whatever that means. We say that this is left exact if for every exact sequence, every short exact sequence, 0, A, B, C, 0. Now note that when I apply my functor F to this sequence, zeros will get mapped to zeros. Let us fix that. And A will get mapped to some FA, B will get mapped to some FB, C will get mapped to some FC. So I'll just write that down. And what I specified earlier is that arrows also get mapped to arrows. So I'm not specifying much, but like if there was some small f here, this would be f applied to that small f. Anyway, so the point is we will say that f is left exact if the exactness of this sequence implies this sequence is exact. So the point of removing that 0 is now I only have to consider exactness at fa and exactness at fb, but not exactness at fc. And similarly, we have the same thing for right exactness. So f is right exact if for every short exact sequence of this form, remove this, draw back the 0, if that sequence is exact. So there it would be exactness at fb and exactness at fc. And then we will say that a functor is exact if it is both left exact and right exact. Result 1 is left exact. This is not a hard proof. If I had more time, I would have proved it, but yeah, you can try doing it. This is not actually not bad, but I'll just state it. I mean, you can write out the definition, but all this means is that if 0, f, g, h, if this is exact with these maps, this is implies that 0 on mf alpha star on mg alpha star on mh. This is exact. I mean, I've just written out the definition of what it means for a functor to be left exact, but yeah. And now the point is, form is not right exact in general. So now we have the first and one of the few examples of this stuff. So consider this exact sequence, and also because it is an example, it is one of the few instances where instead of working with an arbitrary commutative unital ring, we will be working with Z. In fact, I think the only two instances I'll be working with Z. Depends. Let's see. So consider this exact sequence. This is the map where you take where you fix some integer n. Okay, fix n. I'll let n be non-zero. Yes, I should point that out. And then let this be the map given by multiplication by n. I guess non-unions and probably just to. We don't want trivial examples essentially, but fix some integer n. Let this be the map given by multiplication by n. You can verify that this is a Z-module homomorphism, and this is simply the projection on Z mod n Z. This is the fact that this is exact. You don't even need to look at this part. This part is surjective, and the kernel of this map is precisely those elements which are the multiples of n essentially. So that is clear why this is exact. Now, if we apply a form, we will apply a form Z mod n Z as a Z module. So 0. These are same n. Sorry. This is pi star. This one is not relevant. So, my claim is that this is not right exact. If it were right exact, that would imply this pi star were surjective. That implies that the image of pi star is isomorphic to this module. Now, what is the image of pi star? Before we look at the image of pi star, what is distinct here? From Z mod n Z to Z. So let us pick some element here, say f. So this is an R module Z module homomorphism from Z mod n Z to Z. So, and this is cyclicity, whatever argument you want to give. Because it is an R module homomorphism, specifying where 1 plus nz goes, will specify where all of Z mod nz goes. So let us just take a look at that. And now let us set it to some t in z. But then f of 0 plus nz is the same as n plus nz. That we get back to nt in z. This is the zero element of z mod nz. So this has to be the zero element of z as a z module, which forces nt to be 0 no matter what n you choose. So t is forced to be 0. T cannot be anything non-zero. Equal to 0 as f is a morphism. So t has to be 0 to begin with. However, because t is 0, everything in z mod nz is going to map to 0. Therefore, f has to be identically 0 no matter what f you take in this module, which shows that this module is simply the 0 module. We have shown that this is the 0 module by whatever I did just now. Which shows that the image of pi star, image of this under pi star is simply the 0 module. However, if this were right exact, that would imply this module here is the 0 module, but that cannot be true because the identity element has to be there no matter what else is done. So this shows that form functor form m dash is not right exact in general. This motivates the following definition. M is called projective if M is right exact. So whenever it does happen to be right exact, we said that the module for which it is right exact is projective. And by that result one I believe I called it, hom is left exact for arbitrary m. So if your m happens to be projective, then hom is in fact an exact functor. So short exact sequence, we apply hom, you get a short exact sequence again. This is the definition. Equivalently, if you just write out what this means, given, I'm not sure if I specified this. When I say surjective module morphism or injective module morphism, I just mean that the underlying set maps are injective and surjective respectively. Maybe I messed up the order. Anyway, and when I say that it is an isomorphism, I just mean that the underlying set map is a bijection. Equivalently, E projective can only given a surjective morphism from A to B and a map from P to B, there exists a map from B to A such that the following diagram commutes. This is that map. I guess I should have named them to avoid ambiguity, but I think it's clear from the statement. This is just a restatement because what happens if hom is right exact? Look at this thing. Ignore this P for a moment. This is an exact sequence precisely because this thing is surjective. Now because this is surjective, we apply, because this is exact, we apply hom, and now because P is projective, that new exact sequence, the new sequences will also be exact. So hom MA, hom MB, 0, whatever is in between, this thing, okay, fine, I'll name it like this. So F star is going to be surjective, which implies that any module morphism from P to B, which is precisely this, is in the image of F star, which is the collection of module morphisms from P to A. So this is not surprising. But now there are some actual characterizations. This is just a restatement of the definition. Again, this is another result that I would have liked to prove, but time does not permit. the second one is clear. What this means is that M directs some other module Q is isomorphic to some free module. These proofs are also not bad. I will give references for most of the things. You can find proofs in geometry and code, not all of them, but if you want to look at the proofs, talk to me after the talk. I'll point you to some references. This I am not going to prove, I will assume it. However, as a corollary, free modules are projective. Right? Let us look at the second condition. Towards the beginning, when I started talking about free modules, I proved the result that every short exact sequence 0 A B F 0 splits where F is free. But that is precisely an equivalent condition for the module to be projective, as I stated here. But this just implies that free modules are projective. Next, right, bilinear maps. So let us fix to our modules M N. Now, if P, sure, let's fix P as well. We say set map. This is not a module morphism. F from M cross N to P is R bilinear. Going forward, I will only be saying bilinear because once again, same ring. If these two, so the point is that if you fix one of the coordinates, the induced map should be linear, and that is precisely the definition. M to P are linear for all M in M and N in M. The point of talking about bilinear maps is to talk about tensor products. Now, this I'll try to spend some amount of time on because I know it has not been covered in the second year course yet. So again, let us fix to our modules M N. Now, what I will do for the tensor product, I will define it by the universal property. The issue with that is, I can define whatever I want. That does not show that the tensor product of two modules exists. That is given by the construction. I have the construction written down here, but I do not think I have the time to talk about it. It uses two facts, essentially, that if you have a map from the basis of the free module to some other module, that specifies the map from the free module, as well as the universal property of the quotient for the uniqueness of the universal property. But that's fine. I'll just say what the universal property is because that is in some sense the most useful part. Also, it is the most useful part because M tensor and even in the construction, that the standard construction, they are not actual. They end up being equivalence classes of an equivalence relation that is defined on the free module indexed by the Cartesian product M cross N. So if you have, say, M tensor N, whatever that means, if that is equal to the 0 of the tensor product, you cannot say anything about M and N individually. It does not give you anything. Or even if you have something like M1 tensor N1 is equal to M2 tensor N2, this expression is useless. It does not tell us anything. We cannot do anything with this expression. So the construction is not particularly helpful in 90% of situations. So all I will do is, given to modules M and N, there exists an R module M tensor N and a bilinear map from M cross N. This is the direct product of these modules. I know I did not define direct product, but you know what finite direct product and finite direct sum are the same, so just take this as the direct sum of MMN, but like represented differently. It is isomorphic as modules to this thing, so technically I have not missed out. It's fine. And a bilinear map from this direct product to M tensor N, I'll call this I, satisfying the following universal property. Let M cross N to F and T, this map F be bilinear. Then there exists unique F tilde from M tensor N to T linear, making the following diagram commute. Again, the same thing that I mentioned at the beginning of the talk. The collection of objects that make the diagram commute. Which diagram commute? Forget this part. So M tensor N is going to be some object making this diagram commute, which simply collection of bilinear maps, some bilinear map from M cross N to this module. And similarly, T is another object making the diagram commute, in the sense that there is a bilinear map from M cross N to T. And we are just putting the initiality condition that M tensor N is that object which is initial with respect to making these diagrams commute. And in some sense, this is all you need for the tensor product. What it is telling you that if you have a bilinear map from the direct product of two modules to some other module, you can factor it as a linear map from the tensor product to T. This is in some sense the property of tensor product that people usually want to emphasize, that it allows you to factorize bilinear maps or in general multilinear maps into linear maps from the tensor product. I have some more comments about the tensor product. I have an example. The example will probably not be accessible to everyone, but I'll just state it because often people are like, what is the point of tensor product? Sure, there's an example. Read up on the background if you have to. Let B, W, B, F, E varieties over some field K. Then the coordinate ring of the product of the varieties is isomorphic to the tensor product of the varieties. Isomorphic to the tensor product of the coordinate rings. This example is for those who understand it, but it doesn't really matter. I have a slightly better thing to talk about, which in some sense is a generalization of this. So, the tensor product, it allows us to do something called base change, essentially. What do I mean by base change? Let M be an R module and let A be an R algebra. What is an R algebra? An R algebra is simply a ring A with a ring homomorphism from R to A. This puts a natural R module structure on A in the following way. R dot A, you just define it to be phi R times A. So because A has a natural R module structure, we can take the tensor product as R modules. I should write it like this. But A also has a ring structure of itself. So there is some way, I don't want to spend much time on base change, but like there is a way to interpret this tensor product as a module over A, which is quite simple. A dot A tensor M. Okay, this is verbal notation. On this A naught, sure. We define it to be A naught A tensor M. Also, I am representing elements of the tensor product by these elements A tensor N. Every element of the tensor product of naught is not of this form, but these are the basis of the tensor product. So, writing down the maps for the basis elements justifies it, just extend linearly. And this puts a module structure on this tensor product. So you start with an R module, you start with an R and an R algebra, then you can treat the tensor product as a module over the algebra. This is the idea of base change, and in fact this is the idea that goes into proving this statement. And another comment I will make that is also quite useless, at least it is just a restatement of the universal property. But if you know what representable functors are, then the tensor product for two fixed modules m comma n is simply the object representing this functor. So this is a functor in the sense that each module is sent into the collection of bilinear maps from m cross n to that module, and then a map bit from m. So a map from bilinear m cross n z1 to this map is simply a module map from z1 to z2, making this map complete. But if you don't know what representable functors are, it's a waste of everyone's time. Let's not talk about this and move on. Next.
Can you go over the definition of algebra?
Let A be a ring. We say A is an R algebra if there exists a ring homomorphism, as a strict morphism for short, from R to A, call it phi. So this is all. This is an A algebra is simply a ring with a morphism from R to A, and this gives it a module structure, R module structure in the following way. So what do I mean by R algebra structure? The ambient group structure is only there because it's a ring. So all we need to do is to define the scalar multiplication structure. So let me take some element, some scalar, and let me take some element of whatever we want to turn into a module, and I will just define it as phi R. Now phi R is an element of A and multiplied by the element A. And one can verify that this puts an R module structure on A. Right. Once again, like we discussed functoriality of form, we are now going to discuss functoriality of tensor. So in the same way that linear maps from A to B induce a linear map from Hom M to Hom M B, we have the same thing for tensor product. So fix M. Let A, B be R modules, let F be a module morphism. Then there is a very natural map from this direct product to this direct product. I'll denote it by F cross 1, where you just send the pair A comma M to the pair F of A comma M. And by universal property of tensor product, this as the natural map into the tensor product M. This is just F of A tensor M. And this is denoted, okay, no, this is not denoted by anything. So the comment I made earlier that universal properties allow us to build maps out of maps that we start with. So what I'm trying to do here, I'm essentially trying to build a map from A tensor N to B tensor N using this F. So to specify a map from the tensor product of two modules into some other module, I need to specify a bilinear map from the direct product into that module. So that is essentially what I have done. I have specified a map from A cross N to B tensor N. However, one needs to verify that this composition is in fact bilinear. That I will leave it as an exercise. Yeah, I think that I'll leave it as an exercise. One can verify that that map is bilinear. Also another thing which is slightly different, which I will also leave as an exercise. L composed B is bilinear, where L is linear and B is bilinear. But anyway, back to what we are doing. This gives us a bilinear map from this direct product to B tensor N by the universal property of the tensor product that induces a natural map from A tensor N to B tensor N. This the notation will be f tensor 1. 1 just means identity in the sense that second coordinate is not being affected. Because n is anyway fixed, we don't want to change n. And this is just given by, one second, I'm specifying it for the basis elements. Not all elements of A tensor M will take small a tensor small m. So now, once again, what I said a functor was, it sends objects to objects and maps between those objects to maps between your new objects. And that is precisely what we have done. You fix M, and then you can send each A to A tensor M and each map F to F tensor 1. And we can discuss exactness of this functor. The same way that we discussed exactness of form. And that is going to lead us to there eventually. So the two axioms, identity maps to identity and commutative triangles go to commutative triangles. So the first one, so A to A, the identity map, then identity composed one. Right, I should have specified this for talking about tensor product. But because I am working with the same ring, I am not bothering with specifying what ring we are taking the tensor product over. But M and N are modules, so usually you should denote it by a small r. When you take tensor product of vector spaces, then you denote it by a small k underneath. If k is the field over which the vector space is defined. But the point of this is that when you do things like base change, or you get a proof of this thing, what happens is that you consider it as a tensor product over your field k, and then suddenly you will consider it as a tensor product over some other algebra, some algebra of polynomials. So there you should specify in this way what ring you are taking the tensor product with respect to. But here I am not bothering because it's the same thing everywhere. So the induced map from A tensor M to A tensor M. This is identity tensor 1. So the basis elements are just going to map to identity on A, which is just A tensor M, which shows that this is nothing more than the identity on A tensor M. And secondly, G composed F tensor 1 is the same thing as G tensor 1 composed F tensor 1. What I mean by making triangles commute is that, so functionality is, this is the second axiom just in general, that if you have a triangle like this, then applying your functor should preserve the diagram. This is the second axiom of functionality. So these two things, I'll leave it to you guys to verify. It's not hard, both of these. You can get it from this thing essentially. Both of them will follow from here. And then another result that I will not prove, tensoring. By tensoring, I just mean tensoring by some fixed M module, by some fixed R module M is right exact. What this means is that if you have an exact sequence, short exact sequence 0, A exact implies A tensor M, B tensor M, C tensor M, 0 exact. So you can sort of see how this is dual to whatever we did for home. Home was in general left exact, not right exact in general. Tensoring is right exact in general, but it will not be left exact in general. And this will be the second example, which will look quite similar to the first example. So consider essentially the same exact sequence. Instead of n, I'm just, for whatever reason, I've picked a particular n. I think you can do the same thing, but let's just stick with this. This is simply our quotient map. And then we will tensor with z, in fact. So I'll I'll denote this as z tensor dash. So 0 c. Wait, something I have messed up. We are not tensoring with z. We are tensoring with z not to z. Sorry. Now, okay, elementary fact that I should have mentioned earlier. R is always the same R ring is a module over itself, and let M be an R module. Then this you can show to be isomorphic to M. We use this now and we'll use this again later on.
Does the fact that cancelling is right except and then does the fact that I mean the word cancelling tensor on the right hand?
Yeah, for tensor it does not matter. For tensor it is symmetric. For Hom, it will still be left exact depending on what you mean by left exact. So the arrows are going to be reversed because Hom dash M is contravariant, but that depends on what you mean by left exactness. So by left exactness, do you mean left with the arrows reversed or with the arrows in the same direction? But it is still the same. It will not be affected. It will not affect the behavior of Hom. Essentially, is what I'm trying to say. Take this as an exercise. This is actually not planned. For this, try using the universal property and that remark I made earlier that if you have two objects satisfying the do it again. I have not done that yet. I think I'll discuss that. So I'll do it for the universal property of product, but you can extend this proof to any universal property. Once again, the formalism of limits and co-limits would allow you to do it in general in one go for every universal property, but I'll just do it in particular. So what should we do? We should do product, fine. So let us fix two objects x and y, and let A and B be products for the pair xy, for xy. This. What I mean by this is that there exist maps from A to x, A to y, such that for any other pair of maps from z to x and z to y, there will exist a unique module homomorphism from z to a. Okay, fine. Here we can take module homomorphism. Product is nice enough where we can do product in arbitrary categories, but for the sake of this talk, I'll restrict ourselves to modules. So if you have two R modules x and y, and what it means for an R module A to be the product of x and y is that there exist maps from A to x and A to y such that for any, this z is arbitrary, z and these two maps are arbitrary. For any maps, for any object z with maps z to x and z to y, there will exist a unique module homomorphism from z to a, making this diagonal commute. This is all it means for A to be the product of x and y. So b is also the product for x and y. So z to x, z to y, b. Note that these maps are not arbitrary. These maps come with your objects A and objects B. These maps and this object is arbitrary. And now, precisely because these objects and this object and these maps are arbitrary, I'll just take this object to be A and along with A's canonical maps. So, for the case of product, you would think of these as projection maps because what do we have for A cross B? Sorry, not equal to x cross y to x. So the canonical projection map is given by this thing. In this case, this would be this map, and the other thing from x cross y to y is any xy to y, that would be this map. If this was the standard x cross y, and these are the maps that we use to show that the normal Cartesian product of x and y satisfies the universal property. That's all right. So first we will apply universality of B. By universality of B, there exists a unique f making this diagram commute, and then the same thing the other way around. By universality of A, there exists a unique G making this diagram commute. Now, note that we can join these two diagrams. So I'll compose G and F essentially to get a commutative diagram. This is G composed F, I believe. Yes. trivial way to make this diagram commute by putting the identity map here. What the universal property tells me is that the map from here to here, because of the universality of A, is unique. In the sense that for any other map that makes this diagram commute has to be this map. But identity makes it commute trivially, which implies G composed F has to be the identity on A. And similarly, F composed G is the identity on B. And this shows that A and B are isomorphic. And you can mimic this proof for any universal property, because every universal property you will get some sort of universal morphism essentially between your universal objects. Why did I talk about that? Right. Use that to prove this. Show that M satisfies the universal property for the tensor product R tensor M, which shows M is isomorphic to R tensor M automatically. Okay, yeah, I was trying to show this is not left exact. To show this is not left exact, I have to show that this is not injective. So why is this not injective? Let us look at this map. This is multiplication by 2, tensor 1. So let us look at what this does to an arbitrary element. This is equal to 2n tensor m bar. Because of bilinearity of the tensor product, this is the same thing as n, and both of these are Z modules. So we can take the 2 out and then take the 2 into the other quadrant. So 2m bar, but 2m bar is 0, and tensor 0 is 0. That comes from the maps itself, I guess. That I don't really need to just the bilinear map something comma 0, it will map to 0. Yes, I think that's true. Right, because it has to be linear in each of the coordinates. So even under the bilinear map, it's going to map to 0. The point is, no matter what you take, it's going to map to 0. So the kernel is all of this, but this is not trivial because by that result, this is isomorphic to Z mod 2 0. And this is obviously not the 0 module. So this shows that tensoring is not left exact in general. Now, what did we do in the case of Hom? Hom was not right exact in general, so whenever it was right exact, we call those modules projective. Same thing we'll do here. Anyone call it projective? That will be ambiguous. We said M is flat if tensor then is left exact. So what this means is that now tensoring will preserve injectivity. Earlier Hom did not preserve surjectivity, but for projective M, Hom does preserve surjectivity. Same thing will happen here. Not the same thing, the analogous thing. The earlier injectivity was not being preserved. This is an injective map. Right, this is an injective map, that is clear. 2n equals to n implies n equals to n in the integral domain, whatever argument you want to apply. But now this is clearly not injective. So injectivity is not being preserved. But when injectivity is in fact preserved, we will say that it is a flat module. Again, same thing that a comment I made for Hom as well, that it is right exact in general. So if it is flat, it is left exact as well. So for flat modules, tensoring is exact. One more result that I will not prove. And now we are getting to the crux of the talk. M is flat if and only. Okay, I'll have to make a definition, talk about this. So I already defined free modules. A free module of finite rank is something for which the indexing set of the free module is finite basis. If the free module has a finite basis, then we say it has finite rank. It is a free finite module. I'll use notation. I'll say free finite, finitely generated free. All of them will mean the same thing. Definition: finitely presented. We will say that M is finitely presented if it is the quotient of some free module where such that J finite N finitely generated. Given and a map f from E to M, there exists a factorization. What do I mean by that? I'll write it down. So what I mean by factorization is that there exists maps H from P to F and G from F to M such that this diagram converges. That is all this means. I will not be proving this result. Okay, now we will come to a new universal property. And the following universal property, there is a very nice example from algebraic geometry that I would like to talk about, but I think I'll talk about it if I have time at the end of the talk, after I prove the theorem. In fact, I'll write down this result on one of the boards on top because I'll refer to it eventually. Right, I think I missed out the most important part of the theorem. F. Where F is free of final rank. Directly. So I will assume all of you know what partial ordered sets are. It is just a relation of a set which is irreflexive antisymmetric transitive. There is no point about the ambiguity of whether we should take it to be reflexive or irreflexive because I'll be working with less than equal to anyway. So if you want, you can just assume that in particular less than is the partial order and then, but I will not bother with such elementary. I will just say opposite is directed, which is more important. If for I, j in I, so you pick two arbitrary elements from your indexing set. Okay, not indexing set, your poset. There exists k in I such that it is greater than equal to both of them. Why something like this is required will become clear soon. The directed. So we take a directed system, and this is going to serve as our indexing set essentially. My mu I j is set. Okay, I should write what a mu I j is, I guess. Mi index by I culture of modules. So whenever I is less than equal to j, there is going to exist a module morphism from mi. Well, not there is going to exist, but this is the setup essentially. That whenever I is less than equal to j, there is a module morphism from mi to mj, which is going to be denoted by mu ij. Then this collection of modules and morphisms is a directed system. Right, no, it's a directed system if the two following conditions hold. And these conditions should remind you of something that I have talked about twice earlier. The reason for writing this in this obnoxious manner is that you should think of mu as a functor from this partially ordered set to your category of modules. And this is how you, this is a particular way to realize direct limit as a colimit. So what is a colimit is, I'll just talk about it for a few minutes I guess. A colimit, you have some indexing category and then a diagram in whatever relevant category you have is a functor from that indexing category to this category that we care about. In this case, it is the category of our modules. So here our indexing category, I'm not sure how many of you will be familiar with this, but given a partially ordered set, there is a standard way to put a category structure. If I is less than equal to j, you define a unique arrow from I to j. This automatically gives the identity morphisms as well. But anyway, so if our indexing category happens to be a partially ordered set which is directed, the colimit turns out to be whatever I'm going to define as a direct limit. And that is why these are precisely the functoriality axioms. That the identity, so I less than equal to I is precisely the identity morphism. So the object corresponding to that, the morphism corresponding to that is the identity morphism, and triangles go to triangles. So this is a directed, this is what I define to be a directed system of modules, just a collection of modules and maps between them, such that these two axioms hold. Now, for the actual direct limit. So, consider these MIs as sets for the moment. I'm going to strip away the module structure, I will put it back together again. So consider the disjoint union of these sets. Whatever formalization we have of disjoint union, we can, so when the sets are disjoint union is the same as union, so I mean this is a set theoretic issue, doesn't really affect us, but we can go by an isomorphism to some module whose elements are distinct from the elements of the other modules and then just take a union to get the disjoint union. That is just formalism, but and then we want to put an equivalence relation on it. So what the equivalence relation is going to do, this is the thing that I talked about when writing down the universal property for direct sum, is that we essentially want to embed these MIs into some big module where the behavior of the elements from these MIs respects whatever these maps do essentially. So we want to compare all the comparison that we want to do in our big module, it should come from here. So the equivalence relation is going to be, so we take two elements in this disjoint union, say Mi coming from Mi, Mj coming from Mj. Then we say that these two elements are equivalent if there exists a k such that mu ik Mi is mu j k mj. So the idea is that if you think of it as a sequence essentially, like a sequence indexed by your, like an ascending chain essentially, if you think of it as an ascending chain, if your elements, if the two elements become the same at some point in the chain, then you want them to be the same here. So this is the equivalence relation, this is the collection of equivalence classes under this relation, and then we are going to put the module structure on it again. So, and this is where the directed axiom is going to come in. So the issue with adding elements, I mean the first issue with adding elements is that I have stripped away the module structure anyway, but even if I hadn't done that, Mi and Mj are elements of some different abstract modules. It does not make sense to add an element of Mi and an element of Mj. But what That's the action. What this allows me to do is that once again, at some point in the chain, I bring them to their corresponding elements in mk, because there is some k which is greater than both I and j. So that is what I do. But now we are in mk. This is a module structure. We'll just add them there and call it essentially. So this is defined to be new ik. And implicitly there exists by this action there exists a case such that which is greater than equal to both of them. So this is an element of m sub k, this is an element of m sub k, you add them, take a image. And this is the module addition. Module multiplication is not that hard, all of them are R modules, so you don't really have to do anything. The obvious choice works. And I didn't even have to write I no point. But essentially this module structure is what we are going to call the direct limit, and the notation that I will use for it is the following. So we will denote that structure by eventually, so this is enough when the indexing set is clear, but at some point I'm going to work with a different indexing set, in which case I will just denote this as I to remove ambiguity about which character system we are working with. Alright, I should mention these. I talked about how we should think of these MIs as being embedded in this disjoint union. So there are clear maps from each MI. Alpha sub I from MI to this disjoint union. Sorry, not the disjoint union. Insert M to you can check that all of these are module homomorphisms. That is not hard. What else? Right. So earlier I talked about for the direct sum is the natural way to put together a certain collection of modules such that in the embedding they remain independent in some sense. But what we are doing now is we are trying to generalize in some sense. These new ij's, they are making these modules interact. So if we were to take the directed system where we just have a collection of modules with no maps between them, then that would precisely end up, the direct limit of that system would end up being precisely the direct sum. I'll write it down, take that as an exercise. I'm writing it in chat. No point writing down details, I think those of you attending will know what I mean. No mu ij implies is the same thing as, again, try doing this by the universal property. In fact, this is trivial using the universal property because look at what happens. Oh, I have not specified the universal property yet. You know what? We'll come back to that exercise. The direct limit satisfies the following universal property. Again, let me recall whatever I said earlier. So we have collections of objects making certain diagrams commute, and then we impose either some initiality or finality condition and call that our universal object. So here, limit is collection. So suppose mi mu ij is some directed system of modules, let the limit will be denoted by this thing. Then this collection satisfies the following universal property for any collection C phi i's such that making the diagrams from you. Or I should draw the diagrams. What are the diagrams? So these are not particular ij's. These are arbitrary ij's. So for all ij's. There is this unique phi from the direct limit to z such that this thing commutes. And it is an easy verification that if you take z as the direct limit and phi as the alpha is, all of these triangles will also commute. And now this is the initiality condition essentially. I'll rewrite it once on one of the above boards. So this is the universal property that it satisfies. Now we can actually go back to the exercise, but before that I'll just write down the property here. Okay, I don't think there was much point to writing this, but I guess I'll leave it here. So I'll just draw the diagram. I think that is enough to remind us what is going on. But I want you to understand what is going on here. So and this we are actually going to use in the upcoming proofs. There are going to be objects and collections of maps from mi to z, making these diagrams commute. And because of the universal property, there is going to be an induced natural map from the direct limit to that object. We will use this in at least 2 of the proofs, if not more. So the thing I said earlier, we are constructing a phi out of those phi i's in a natural way, whatever that means. So, if there are no new edges, then our diagrams will simply reduce to mi, mj, alpha I, alpha j, phi I, phi j. But this is nothing more than the universal property for the direct sum. Did I erase that? I think I erased that one. I guess I should have left it. It's fine. Result 4 is there, that is there. Next we will talk about, okay, right, this is where I had the example, but I think I'll leave that for now. I'll talk about it at the end. If all of you are ready. So another result I will not prove, but this is a result that all of you can actually try proving. This is not a bad result. Tensor model commutes with direct sum. Use the universal properties. That they will make life much easier. Yes. So what I mean by that is show that one of them satisfies the universal property for the other object, or whichever way you want to do it. I think it's for the most part the same thing. But essentially, if you manage to show one of them satisfies the property for the other, by the argument I did on that board for the product, it shows that the two objects are isomorphic, and the isomorphism is natural with respect to making all the natural maps commute. Okay, now we will actually start with, okay, not yet. After this result, we will start with that. How much time do I have?
12 more minutes. Okay, take 15 minutes.
Fine, then I will not do this as a assume this. The two modules are flat. Already, three modules are flat. Now we will start doing some actual proofs. Number one, direct limits preserve exactness. What I mean by that, because I am running short on time, I'll just summarize and abbreviate whatever. So suppose we have three direct limit systems, Fi's, Gi's, Hi's. The limits, I should have defined it when doing direct limit, I already erased it. But this thing, instead of writing this thing over and over, I will just write M to make it clear. But to listen whatever I have to write. So suppose we have direct limit systems, Fi, Gi, Hi, and suppose we have collection, like for each I there is an exact sequence from Fi to Gi to Hi, then the induced sequence FGH is also exact. So this induces maps from F to G in a very natural way. How? That's universal property. So Fi, Fj, map from here to here. Let's write this map later on. Let these be the Fi's. These will map naturally into G. Now we have maps from Fi into G and Fj into G, which makes each of these diagrams commute. We are providing universal property of the direct limit. There is a map from F to G, which makes this diagram commute. Call this map F. Similarly, we get a map from G to H, making all of the relevant diagrams commute. And now the point is to show that FGH with F and G make the diagram is exact. Sorry. So for that we have to show that the kernel of G is equal to the image of F. So we will start with something on the right hand side, so it is in the left hand side. So let X plus tilde be in the image of F. And I'll just, now these are what are known as diagram chasing proofs. So let us take something in the image of F. So let's say X plus tilde. Now X plus tilde will be induced by F, induced by some Y plus tilde under F. Now this Y plus tilde is an element of the direct limit, so it is the representative of something in some Fi. So we'll just write down that Fi. So now this Y will map to something in here, whatever that is. But by commutativity of this square, it has to map to Y plus tilde. But because this row is exact, I give a remark this at the beginning that computation of any two consecutive maps in an exact sequence is 0 precisely because of this thing. So Y under the computation of these two maps is going to map to 0. But by commutativity of this, these are module homomorphisms, so this will map to 0. By commutativity of this square, X plus tilde maps to 0 under G, so X plus tilde is in the kernel of G. For the other direction, we just take something in the kernel of G. So say X plus tilde maps to 0 under G. Again, X plus tilde is the representative of some X in some Gi. Say X here. X is going to map to something in here. What should I call it? Whatever, doesn't really matter. But X will map to something in here which is going to map to 0. Now this thing, what this means, this comes from the definition, right, good thing I need to erase this. This definition of equivalence. If something is equivalent to 0, that implies that it had become 0 at some point earlier. So this thing, what I said earlier, that if two elements in the direct limit are equal, that means they must have become equal at some point earlier in the ascending chain, which containing both, okay, it won't contain both I and J, but ascending chain containing Ik and Jk. So if something is 0 in the direct limit, all that means is that it must have become 0 earlier at some point. So I'll denote that by J greater than or equal to I. So this x will map to 0 here. This x is going to map to something. I'm running out of rotation. Let it map to x tilde under this map. By commutativity, this x tilde maps to 0. However, this sequence is exact, and this x tilde is in the kernel of this map, so there must be some z here such that z f of this thing, fj of this thing is equal to x tilde. Now we'll just join these back. These are the inclusions into the derived limit. Now let's see what's happening here. Z maps to x tilde under this map, which maps to x plus tilde under here. So by commutativity, whatever z maps to here, it is forced to map to x plus tilde under f, which shows that x plus tilde is in the image of f, which moves this. These are the lemmas that we will actually be using, so I'll write them down. Direct limits commute with tensor product. What I mean by that is, tensor n is module isomorphic to the limit of these. For convenience, I will denote this by p. So what we are going to do is, I will define a map from p to here and a map from here to p. Using the universal properties, and then I will leave it to the audience to verify that the compositions do in fact give identities. So first we are looking for a map from P to M tensor n. Now we are looking for a map out of the direct product. So by the universal property, it is enough to specify maps out of each of these, making these diagrams commute. So we want a map from each mi to M tensor n. Each mi tensor n to M tensor n. But there is an obvious choice here. Each mi to m there is an alpha I. So this will just take it to be alpha I tensor n. Yes, tensor 1, sorry. And then one can check that this makes all of these diagrams commute. Mi tensor n. M tensor n. These are the alpha I tensor. This is alpha I tensor 1. This is alpha j tensor 1. So by universal property of direct limit, this induces a map from P to this thing, which we have called phi. This will be the first map. The second map, psi, we want it to be from M tensor and P. Now the idea of getting this map is something called Hom tensor adjunction. You have probably seen adjunction at some point, but essentially it allows you to write maps out of the Cartesian product as maps from the first module into the collection of maps from the second module to the third. And that is essentially what we'll be using. We do not really have the time to talk about Hom tensor adjunction in general, so we'll just do it by brute force essentially. The universal property of tensor product, it is enough to specify a bilinear map from M cross N to P. So that is what we are looking for. The idea, bilinear maps from A cross B to C are the same thing as linear maps from A to B cross C. As A to Hom B C. So we have natural maps. These are the natural maps for the direct limit essentially. So the alpha is are the direct limit maps for each mi to n, and the beta is are the direct limit maps for the mi tensor n to the direct limit of the mi tensor n. from NP by sending M to beta I of M tensor dash. One can show that these things will commute. This is J. By universal property of direct limit, this will induce a map from linear map from M to omega P, which I will call gamma. Now this gamma again, what we did earlier, we converted our bilinear maps into linear maps. We use the property of direct product to get a direct limit to get a linear map. Now we will go backwards to get a bilinear map. So define gamma star from M cross to P by sending the pair Mn to gamma n evaluated at n. One can check this the bilinearity, and this induces psi from M tensor n to P by the same thing, M tensor n to gamma n tensor n evaluated at n. So now we have maps in both directions, psi and phi. I leave it to the audience to verify that these two compositions hold. The two levels that we have put so far, they essentially help us to one direction of the theorem. Now the next two will help us to the other direction. What this means is that J is a subset of I, and the posset structure on J is induced from the posset structure on I, and this will also be directed. We say that this will not be directed, but we will say that this is cofinal in the bigger system if for all I in I there exists a J in J such that I less than equal to J. And we will prove a result about cofinal subposets. If suppose J cofinal with respect to EIs, then taking the direct limit of the subsystem is the same thing as taking the limit of the entire system. Again, I will just define maps in two directions and leave it to the audience to verify that they work. So again, we want maps out of direct limits in both cases. So we just want maps from each mi to here and from each mj to here. So from each mj, it's quite obvious. We take just the alpha j's, mj. Commutativity of those triangles will be obvious because these are the things that make the diagram commute in the first place. induces, not induces, induce, there are many of these maps in general. Element J, element and in the opposite direction, by cofinality, this is where the hypothesis is being used. For all I in I, here exists J sub I in J such that I less than equal to J sub I. But I is less than equal to J sub I, so by our definition of directed system, this gives a map from M sub I to N sub J sub I, which maps into the smaller red limit. This, these, induce psi from the entire direct limit to the direct limit of the subset. And once again, I'll leave it to the audience to verify that this works. And completion will give the identity both directions. One last lemma we will prove before we move on to the actual theorem. Given a here now what you learn, you can realize it as a direct limit of finitely presented R modules. So by the work we have done earlier, there is some free module which subjects onto it. In particular, we can just take a free module whose basis is indexed by the elements of our module M. So we'll take that exact sequence. And we are going to construct a directed set and consequently a directed system. So we are going to look at the collection of pairs J, N where J is subset I. So recall the definition of a finitely presented module. Finitely presented module is isomorphic to some direct sum of J many copies of R quotiented by N, where J is finite and N is finitely generated. And that is the why this definition is written in the way it is. So J finite. So this is the numerator of the quotient, and N subset A intersection J finitely generated. I think I'll shorten this proof for the sake of time. I'll just leave everything, every verification to the audience. But and then the poset structure is quite simple. If J contains J prime, N contains N prime, and I'll do the so lamb for lambda equals to J comma N. So now we are defining the directed system of modules. So far we have the directed indexing set. Now we are defining the actual modules and modules. And for lambda less than equal to lambda prime, so J containing N less than equal to J prime N prime, not J comma N less than equal to J prime N prime. We want to have new lambda prime from M lambda to lambda prime. And this is where, I think this is why I wrote down the property of quotient, but I think it would have been quite reasonable anyway. Anyway, one small comment I'll make here. All of these J's are subsets of the indexing set I. So how you should think of this direct sum index over J? Don't think of it as the abstract direct sum completely, but think of it as the submodule of this direct sum in which only the coordinates which are in J are varying and all the other coordinates are 0. That is how you should think of this thing, which is why it makes sense to quotient by L. Yeah. Right, we want these mu lambda primes. So, mu lambda prime, because of the thing I just said, there is a natural injection which is simply the inclusion map from here to here, and this quotients into this. This is m lambda prime, but also this quotients into so. Now, precisely because n this thing is less, n is less, n is a subset of n prime. This induces a map from here to here, and this we are going to call lambda prime. We are almost done with this Lazard. So far what do we have? We have a directed system of modules, and we have the morphisms making it a directed system. So now I just need to specify the alpha lambdas and then claim that m combined with the alpha lambdas is in fact whatever we are looking for. So same thing we are going to do, because here we are comparing elements of the system. Now next we will be comparing elements of m, not elements of the m, but like this will just be m. This will just be indexed by I. This injects naturally into here, which projects onto projects. I don't know why I said into over here. Anyway, I quotiented by k. This is the same thing as m. This induces a map in this direction by property of quotient and correlation of alpha lambda. Lambda is Jacobian. And now the claim is that limit lambda in the indexing set lambda is equal to m. And this you can actually try verifying. This is not bad. Again, use that thing that two objects satisfy the same universal property. So show that m with this alpha lambda satisfies the universal property for this object. And this proves lemma 4. Now the proof of lemma 4, it would have been nice to have on the board, but I will leave that space. I'll just try to select it. I'll just try to push for that. These are all the results that we will need. Now we can start with the theorem. After which you can all go for lunch. I'm very sorry for going over time. So I did realize the proof right now, but I hope the proof of lemma 4 is sort of fresh in your mind, because that is one of the most important ones. That and that one. Lazard 4. Lemma 4 and Lazard 4. So these are 3 modules of finite array. So we'll start with the easy direction, which is let M be the direct limit of some directed system of 3 finite modules. We will show that M is in fact flat. So let us start with, so we just want to show injective maps, go to injective maps under tensor. So let this be exact. First we will tensor with each of the MIs. Now we know that the MIs are flat by hypothesis. Wait, what are you doing? Yeah, right. Sorry, MIs are flat. MI B, and I wrote down as a result earlier. The 3 modules are projective and hence flat. So MIs are flat. So we can tensor by the MIs. Now I will appeal to this one, lemma 1. Direct limit to the exactness, so I'll just take the direct limit to get 0. Exact. Next I'll appeal to lemma 2 over there to get but this direct limit has the M by hypothesis, so this shows that M is in fact flat, which proves one direction. Next we will do the other direction, which is a bit involved, but it should not be too bad with the very powerful result that we have already assumed. So firstly, suppose M is flat. In the construction that I did for lemma 4, we started with an indexing set. We started with this exact sequence: 0, k, r, I, n, 0. So now instead of taking I to be simply n, will take it to be m Cartesian product z. Why this strange choice will become apparent soon. Then we have a surjection. This is a surjection that is here. It was a surjection when I was even m, and now we have even more space here, so even more elements will go to the same element here. For a fixed small m, for every integer n, e sub f of n is going to map to that n. So surjectivity is fine. Equivalently, the sequence is exact. K is simply kernel of f in this case. That's fine. Now, let me write down the indexing set once more, the indexing set for the directed system. So once again, the reason for choosing j's to be finite and n's to be finitely generated is so that we can get lemma 4 and get finitely presented modules. And the point of finite presentation is to apply that thing. are doing two reduction steps essentially. First we have reduced this follows by level 4 is that M is precisely the direct limit of this system. Yes, that is clear. Yes, I should write in lambdas at least. And next we will do another reduction, which is level 3 essentially. So if we can find a so we are trying to find a cofinal system. If we are not trying to find a cofinal system, we want to show that the collection of free finite modules among the m lambdas. So some of the m lambdas may or may not be free of finite rank, but we will construct some things so that they end up being, and then we will show that this subcoset is cofinal, which by level 3 will imply that the direct limit of those free finite modules is the same thing as this entire direct limit, which is in fact m. Well, subcoset is not exactly correct because subcoset is a subcoset of lambda, but I mean a subcollection of the m lambdas. I think it's clear what I mean. Show a subcoset of free finite. There is the definition of cofinality. Free finite modules in cofinal. I'll just recall the definition of cofinality once again, and that is the bare minimum. So J a reduced subset this is cofinal in if for all j in sorry not for all j, for all I in I there exists a j in j such that I less than equal to j. I'll leave it on this board. I think I'll leave it when I have to. Now, so we want to show cofinality. So essentially, what we want to do is given an arbitrary I, we want to find the j in j. Now, j I want to be the collection of indices of all the free finite modules. So for a particular I want to find a j for which m sub j is going to be in fact a free finite module, which is such that j is greater than or equal to 1. So instead of I and j, I'll just write E and E prime because that is the notation I have here. We will show that for some, we will show there exists E prime such that E less than equal to E prime and M E prime free finite completing the proof. So if we show this, we will be done. So let E, wait, this I guess right. So we have already picked E. Now M sub E is equal to this thing finitely presented. And we have a map f sub E from this thing ME to M. What is this map? This map is the same thing that I did in level 4, that Rj injects into the entire thing which projects onto M, and this projects into its own quotient. So there is an induced map from here to here. This is what I am calling Fe. This is that same Fe. I should actually have drawn this diagram a bit higher because I will need it anyway. The point is that now I will finally apply result 4. So what does result 4 say? M is flat, P is finally presented, then F from P to M. Then for a map F from P to M, there exists a factorization like that. So M is flat by hypothesis, and ME is finally presented. FE is a map from the finally presented module to M. So there will exist a factorization from here to F. M G and H are simply module homomodules making this diagram commute. F is free finite. And as you can probably guess, this is the F that we want. So now we are just going to find an E prime for which M E prime is just F. Now I will just rewrite the diagram I wrote once because that will be useful later on. So that is just the earlier diagram for Fe adjoined with this factorization. Drawn a bit to the left, but it's fine. Call this diagram star. I will refer to it, I think, at least once, maybe twice. We will show that F is M E prime for some E prime in the directed cell. F is free finite, so let us pick a finite basis. Now I'm going to do something which will seem a bit arbitrary, but the point is that the choices I'm going to make, they will help a certain square commute later on. So that is the point of what these things. F is surjective. I believe it's probably written down here. Yes, F is surjective, clearly. And okay, I should just write this one.
Sankha, can you wrap up in 2 minutes? Can you wrap up in 2 minutes?
It won't take much longer. 5 minutes?
Okay.
Is equal to N over distinct and the point of writing this statement is that we can choose distinct elements such that IL is not in J for all L and F of EIL is GBL for all L. So let J prime be J union these new indices that we have picked. Define alpha from rewrite some index by J prime to the sentry module F by alpha EI is equal to H EI plus N beta I sub L I in J I equal to IN and let N prime equal to kernel of alpha. Game 1 J prime N prime is an element of the indexing set. So J prime finite is clear. J prime finite, we don't have to do anything. So we have to show that N prime is finitely generated and N prime is in the kernel of F. So for N prime in the kernel of F, consider this diagram. This square, I guess. Now, if this square was commutated, then N prime is the kernel of alpha. So under this path, N prime maps to 0. So by commutativity, under F, N prime maps to 0, which shows N prime is in the kernel of F. However, this square is commutative precisely because our choices of ILs here. I won't bother elaborating, you can verify it. If it is in J, if you take something here which is contained in the direct sum of R index over J, then by commutativity of diagram star, that will show that it maps to the correct thing. Where is it? Yes. So alpha of x is just going to be h of x if x is contained in direct sum of R index over J, and this forms a basis for the rest. So that will also work out essentially. The diagram will commute. G composed alpha will be F. So this shows that n prime is in the kernel of F. Now for finitely generated, I'll just do it here. Recall n prime is the kernel of alpha, which shows 0, n prime, where is it? J prime R F 0 is exact. However, F is a free module, and we have proved this result early on that for a free module, when the free module is at the end of a short exact sequence, the sequence will split. One of the equivalent criterions for splitting is that this injective morphism has a left inverse, which is also a morphism, but this thing is finitely generated, so the images of the basis elements under this map will actually finitely generate n prime, sorry. So that shows n prime is finitely generated, n prime is contained in the kernel of alpha, n prime is trivially contained here, which implies that n prime contained in direct sum index over J prime R intersection kernel F. So this proves claim 1. All that remains to show is that claim 2. Jn less than equal to J prime n prime. So J subset J prime is clear. We don't have to do anything for that one. All that remains to show is that n is less than equal to n prime. So take x in n, which is contained in here, but this is precisely the span of these basis vectors. But each of these is going to go to 0 by the commutativity of that diagram. So alpha x is equal to h of x plus n. But x is in n, so x plus n is just 0, so this is just 0, which shows that n is contained in kernel of alpha, which is precisely n prime. This completes the proof. This completes the proof of the theorem. I'll just make one concluding remark. For the people who are interested, or the people who thought this was interesting, take a look at what are called projective resolutions. What that does is that we use these Hom and tensor functors to create not exact sequences but something called chain complexes of modules, and then we compute the homology at every step. I won't, there's no time to elaborate on what homology of chain complexes is, but essentially we use Hom and tensor to create new functors. The homology functors are called Tord and X respectively, and the point is that Tord and X help us talk about properties like flatness in more detail. It helps you to zoom in some sense and look at the finer details of at what point the module fails to be exact, fails to be flat, or fails to be projective. And all of this is generalized in the field known as homological algebra, where you abstract out of modules and go to abelian categories, and there you talk about chain complexes and then homology of chain complexes, about how you use certain functors to construct derived functors. So in this case, the derived functors for Hom and tensor are precisely Tord and X. And finally, if for whatever reason you prefer these things, you find these things more interesting than algebraic topology, then you can use module theory as an introduction, as an alternative introduction to homological algebra. That is all. Are there any questions? Thank you all for your time, for choosing to spend your Sunday morning here. I'm very sorry. I hope none of you miss lunch. I think you should be able to get lunch in there.
Let's thank the speaker. Thank you so much.
And for references, look at Davidan Cook or Atia. If you can't find it there, talk to me. I'll find the reference.